Okay, should be live. Hello everyone. Oh no, Alexander. I obviously don't know what is supposed to pass. I don't. I just discussed the problems with the authors before the round. Um, I'm pretty sure that the problem is equivalent to mean cost circulation. So I don't know. Spoiler alert. Uh, yeah, I just copied, I guess, the fastest code from USPJudge. Don't know what is like if you just write your own uh, Cosmos flow, will it pass? I'm hoping you can hear me. You can see the screen. Well, yeah, that would be like finding oh, two potentials. I don't know. I don't know why is it like 40,000 times 400. I don't know. Let's try to move the microphone. Is it somewhat better? Maybe. Uh, no, I guess it's in max volume in OBS. So uh, I'm just a quiet guy, I guess. Um, Initial sum of difference of potentials minus, or is it most? Is it? Why would that be true? The weights are up to 1,000,000, right? But the weights are not up to 100, so up to 1,000,000. Okay, let's see. Oh, it is 100. I'm pretty sure. Oh, so the constraints were okay. They were surely changed since the start of the contest because I opened all the problems at the start of the contest, and I remember that it was something different. Like n was up to 250, m up to 1,000, and weights up to 1,000,000. So that's why I didn't want to write my own in Cosmos Flow, uh, because like it's exponential technically. So I just copied something good from library checker. Yeah, in such limitations, it should work. I don't know. Maybe Maybe in the test the constraints are still bigger. It's weird. Yeah. If that's the case, that does suck. Uh, like, but um, well, if that's the case, I'm sorry, but also I'm not responsible for that. I'm just providing content here, uh, telling how to solve the problems. And actually, let's start do that not in on LGM level. So let's go through problems in order. Uh, okay, so let's start with problem A. Um, in problem A, we had a chessboard n by n. Uh, n was up to a billion, and we need to place m rooks on it. Um, and we want to minimize the number of cells that are attacked by some rook. So the first thing you need to, well, you need to remember that the rook attacks row and the column in which it is located. And then you should kind of understand that there will be some attacked columns and some attacked rows. So those are attacked and those are attacked. And then the set of cells that are under attack will be like the union of those rows and columns. And we have a set of cells that are not under attack, which is this rectangle. Well, they will not be like actual rectangles because you can have like some subset of rows that is attacked, subset of columns that is attacked, but the order doesn't matter. So you can kind of reorder the rows and columns and put the ones that are attacked, the rows that are attacked on top and the columns that are attacked on the left. So we will get a picture like this. Then we can see that if we want those cells to not be attacked, it means that the rooks cannot be in the corresponding rows or columns, and basically the rooks can only be in this rectangle. So now the problem is like this. We need to choose x and y such that m is bounded by x times y. And we want to minimize the number of attacked cells, which is the same as maximize the number of not attacked cells. So n minus x times n minus y should be maximized. And here, like, I was sitting for a minute saying, well, I'm kind of sure that I want x and y to be as close to each other as possible, but it is not clear how to prove it. So I think the best way is to kind of trust your intuition here. But yeah, like I thought more about it after the contest, and I think I have proof that is correct, but it is like unusual and unnatural kind of. So the proof for the fact that we want x and y to be as close as possible is the following. Let's say we fix the sum of x and y. Then we also fix the sum of those two values. And we can see that we want to, with the fixed sum, we want the product of x and y to be as big as possible so that it is bigger than m. And we also want the product of n minus x and n minus y to be as big as possible because that's just our condition, our win condition. And both of those things with fixed sum will be maximized when the numbers are as close as possible. That's like the inequality between arithmetic mean and geometric mean. And the condition on those two numbers to be as close as possible and those two numbers to be as close as possible are the same. So like with fixed sum, we want to make x and y to be as close as possible for both this inequality and for our target function. That means that we just want to be them as close as possible. And now that we know that, okay, we just need to choose x and y that are as close as possible, which means that they're either equal or different by 1. And with that condition, obviously, if we increase the numbers, like this target function will decrease. So we want minimum possible x and y such that they're as close to each other as possible, such that their product is at least m, which will be achieved like when both of them are roughly square root of m. So the simplest way to do it is to just calculate square root of m and then like, iterate in small in small zone around square root to check all the x and y that can possibly be the answer. So yeah, x should be almost y, and both of them should be around square root of m. So find square root of m and iterate in a small zone around it to find correct values of x and y. Any questions about problem A? Any comments on the stream quality? Looks like it's working okay. I'm just curious, how much do you generally go with instincts and where you try to prove something mathematically? So me personally is on very fringe position of I don't go with instincts much. Like I listen to them and they try to like motivate what I'm trying to prove, but usually I want to prove my solutions. But yeah, in this problem, like there is a balance of where the problem is supposed to be in the contest by difficulty, and well, sometimes I have the intuition and like I can like assign some value of how much I trust that intuition. Like here it was kind of obvious that it should be like that. I couldn't find a simple way to prove that it must be that way. But like I still believe that it should be true. That they should be close. So in this case, yeah, I just abandoned the proof and just wrote it. Like it's the first problem in the contest. It should be easy, right? But it's not always the case. And I mean, sometimes the problems are just tricky. And there are definitely wide range of opinions on that matter. There are very successful competitive programmers that just don't prove almost anything. They just trust their gut. That's it can work too. I don't understand how it will work for me, but I know that it is a viable strategy, depending on the person. And actually, I recently, I tried to at least make a conscious effort of allowing myself to believe in some unproven stuff more, because I know that some problems are easier when you believe in unproven stuff, and I know that my threshold of believing is very, very low or high, depending on what is 0 and what is 100. I tend to not trust in random, unproven, greedy ideas, but sometimes that leads to worse performances. Any other questions? Alright, in this case we will move on to problem B. Problem B was about the 2026 string. So we were given a string of length 2n, and we want to split its elements into n pairs, n non-intersecting subsequences of length 2, such that each subsequence is either 2, 0, 0, 2, or 2, 6. We are given a string, we just need to say if it is possible or not. So we can see that in every option there is exactly one digit equal to 2. So exactly half of the characters should be 2. If that's not the case, we can just automatically see that it is not possible. And if it is the case, then all those n2s must be in different pairs. And we can see that zeros can be on either side of a 2, so they're kind of free. For every 0, we can just take some 2, which we guaranteed that they will have enough to go. So we can kind of ignore them for now. What about 6s? Well, for 6s, the corresponding 2 must be on the left, so it's kind of like correct bracket sequences. For every 6, the corresponding 2 must be on the left. So we need to make sure that on every prefix there are number of 2s is at least the number of 6s. Otherwise, for 6s on this prefix, we can only use 2s that are also on the prefix because they must be on the left, but there are not enough of them to go. And if this condition is true for every prefix, then yeah, we can always do that. Just maintain we can go left to right, maintain a set of available 2s. When we encounter a 2, we add it to the set. When we encounter a 6, we just match it with some previous 2. Since the number of 2s on every prefix is at least number of 6s, we will be able to match them, and then we will have some left out 2's, and all of the zeros we can match them as we wish. So if those two conditions, like this one and for every prefix, the number of 2's is at least the number of 6's. If those two conditions are satisfied, then we can always construct the pairs, and we just need to check those two, which can be done in linear time. Easy enough. Any questions about problem B? I think there was also some question when I started problem B. I decided to not break it, but if you're still interested in the answer, you can ask it. Much easier than A, I think. Yeah, I agree, kind of. Well, like in A, if you trust the instinct and your instincts are correct, then it is quite simple. But like to build the solution step by step while being sure about your every reduction you're doing, yeah, I think B is easier than A. Okay, problem C. What was it about? It was about XORs, right? We had some sequence of numbers. We can take two numbers out of the sequence. So take AI and J and remove both of them, but then insert their XOR back into the sequence. We need to do that operation exactly n minus 1 times, so in the end we will obviously have just one element. And we want to do the operation so that at any moment the newly inserted value should not be 0. And as like the output format actually kind of gives a small hint that this means that AI should be not equal to AJ when we take them. Right, so we need to do this operation n-1 times. We want all the inserted values to be not equal to 0, and we need to say is it possible or not, and if possible, then actually construct a sequence of operations. Okay, there are some simple cases when it is impossible. First of all, we need to understand that XOR operation is very nice, and when we basically XOR is like transitive, and it's a group operation, whatever, transitive, symmetric, all of the things. So basically, we are like merging the numbers using XOR. In the end, we merge everything into one number, so the last number we get will be just equal to the XOR of all the initial elements. So this is the last number we will insert. And that doesn't depend on the order in which we apply the operations. You can say that like the total XOR of all the numbers in the set is always constant. So when we have just one number, that must be the number. Or you can say that like we are merging numbers and then we have everything merged, so the XOR must be like that number must be XOR. Whatever way you are saying that, we can understand that this will be the last number inserted. We cannot change it in any way. And if it is 0, then we cannot do anything about it. Like we can try to avoid inserting a 0 up until the last iteration, but on the last iteration it will be 0. So if the XOR of all the numbers in the array is 0, it's bad. So calculate the XOR. If it is 0, just print null, and now we will assume that the XOR is not 0. Okay, the XOR is not 0. It means that the last number we insert will not be 0. Great. Yeah, now we can turn our attention to reformulation of the properties that we want. That the two numbers we are choosing to merge must be different. So there is another simple case when it is clearly impossible. If all the numbers are equal at the start and n is strictly greater than 1, then it is also impossible because it's impossible to do the first operation. In the first operation, we have to choose two equal numbers because all of our options are the same. So in this case, it is also impossible. And yeah, this is an important corner case. I don't actually know if it was present in the tests. I would hope so. So yeah, if n is 1, then the answer is yes, and you don't have to do anything. Oh yeah, it was present in the sample. Sure. Then if n is greater than 1 and all the numbers are equal, it is impossible. If the XOR of all numbers is 0, it's also impossible. Otherwise, it turns out that it's always possible. How to get to this conclusion? Well, you can try to like guess it. It seems reasonable. We have like a lot of freedom at what we're doing, and you can try to, I don't know, write some brute force, generate some tests, and see that it is always possible if those two cases are not satisfied. But in any case, like it's a reasonable assumption. It might seem that it doesn't really help since we need to actually print the sequence of operations. And well, it is true that the problem would be much simpler if we didn't have to restore the answer. We could just believe in this and get accepted. But making this assumption, making this guess, is good because like proving it is like when you know what you want to prove, the life is usually easier. And in this case, if we like believe in this, then the way to prove it would be, well, by induction. Clearly, because like with every move the number of elements is decreasing, so basically we can like prove it for all the arrays of size 2, 3, 4, 5 and so on, and then to make the induction step we just need to prove that uh, if the conditions are satisfied, it is always possible to choose two numbers to make a move on, such that after the move they're still satisfied. And actually, if we provide an like a constructive algorithm of how to find those two numbers uh, fast enough, then it will provide a full solution to the problem, because like all we need to do is do one step at a time. Do one step, get a smaller problem, repeat until you like run out of numbers except one. Um, so okay, what we need to do now is to find a way to make one move such that those two conditions are well. Um, I wrote them differently. So if the XOR is 0 or all the numbers are equal, it is bad. So we want this to not happen and this to not happen. So it is not true that all the numbers are the same. So the first condition you cannot break. Like that condition exists because the XOR is the XOR of all numbers in the set is constant. So if it is not 0 at the start, it will not be 0 at any moment, whatever you do. So we can ignore this. And the only thing we need to do is, so we have an array of numbers that are not all equal. We need to choose two different numbers. Then we remove them, insert their XOR back, and we want to make sure that it is still not true that all the numbers are equal. Okay, great. So we have our array. How to do that? Well, let's try to choose just any two numbers. Let's take those two. Then we remove them, insert the XOR, and all the remaining are the same. So if not all of those numbers are equal, great, we are done. So the only thing, the only situation when it is bad, when all those numbers are equal. That means that all those numbers were equal in the start, and the XOR of the first two are the same as the rest of the numbers. Okay, if that happened, well, I guess we need to try some other numbers to insert. So I don't know. Let's try A1 and A3. So what will happen in that case? A2 will be still the same. Then we have A1 XOR A3, and then like A4, so on AN. Okay, is it possible that all of those numbers are also the same? Well, how would that be possible? That means that A4 through AN are still the same, and like all of them are equal to A3. And those two must be equal. So A1 must be 0, which is impossible. So we are done. Well, not exactly. We kind of tricked ourselves here. Because those numbers might not exist. Like we were using that numbers A4 through AN are the same in this in those cases, and it means that all of them must be equal to A3, and then those two numbers must be the same. Well, if there are no numbers here, then we did something like divide by 0, right? Like we said that A3 must be equal to all of those numbers which are non-existent, and then all those numbers which are non-existent must be equal to this number, which means that A3 and this number are equal. Not true. Like that's how you prove that like 1 is equal to 2, right? You say that let's take an empty set. All of the elements of this set are equal to 1, and all of the elements of this set are equal to 2. It means that 1 is equal to 2. Well, not quite. So if those numbers do not exist, it means that n is at most 3. And we can see that if n is 2, then it's just numbers. We just insert the XOR. That's great. If there are 3 numbers and those are equal, it means that their XOR, like if we take this number and then XOR a3, it will be 0 because this and this are equal. So the XOR of all our numbers is 0, which we already checked and ruled out. So this is also impossible. So okay, the solution is to just take any 2 numbers that are different. Yeah, we cannot take the same numbers. We need to take 2 different numbers. Yeah, I guess it could also happen that a1 and a3 are the same. But again, we can show that that's not true. Basically, if a1 and a2 are different, then one of them is not equal to a3, so just take those 2. Okay, but we also need to like somehow check that happened. Like we just want to take 2 numbers, take their XOR, check if it is equal to all the remaining numbers. If it is not, then it's a good operation and we just do it. If it is equal to the remaining, we need to take some other 2 numbers. So how to do that and how to check it efficiently? Like we cannot afford to run through all the numbers on every iteration because that would be n squared. Instead, we can maintain a map. For basically, we will maintain our set as map of element and how many times it appears. And when you want to do one move, you take 2 elements of that map, kind of remove them from the map. Then how this situation can happen? Well, those 2 numbers must have occurred exactly once, and all the numbers that are remaining in the map are the same. So in the map it will be just 1 element with like size n-2, and it is equal to the XOR of those 2. If that doesn't happen, if it is not true, then just taking XOR of those 2 elements is good. Otherwise, we just have 3 different elements in the map, so we can do it in like linear of number of distinct elements, which is just 3, so it is constant type. That's it for problem C. Any questions about problem C? And there was a lot of activity in chat, so I will look at it. While maybe you're asking more questions. In C, my idea included handling duplicates together, but it failed in case like 1, 1, 1, 2, 2. Well, depends on how you want to handle the duplicates together. Because, well, my solution is handling the duplicates together, but it doesn't fail in this case. I'm biggest Unique fan. Well, thanks, I guess. Although I do not think that anyone who says that is saying a true statement. I start elements in multiset, then take min and max element and XOR of it in multiset, but it failed for few test cases. Well, yeah, because it is not correct, I guess. On a test like 1, 2, 2, 3. If you take 1 and 3 and insert there XOR into the set, it will be 2 to 2 and you lost. But it is possible. So there is no reason to say that taking minimum and maximum is better than taking any two elements, because like XOR does not maintain order. So like I guess you're taking minimum and maximum because you are sure that they're different, and that is easy to do with multiset, but it doesn't have anything in common with solving the problem. The fact that you can do something doesn't mean that it is a correct solution. Hello, Nick. Nick is not my name, and I really don't like when people call me Nick. Please say Nick. Then we have some unindented code from the same person who took min and max. Okay, it is just an implementation of incorrect solution. Yeah, it doesn't work. It is a correct, as far as I can see, a correct implementation of an incorrect solution, so it should not pass test cases. Hi, I solved A, very happy. Good for you. Congratulations. No, I know that everything I say sounds like sarcasm, but you need to start somewhere, and solving a problem is better than not solving a problem. So solving problem A is good. Congratulations. Are you gonna solve the problem F? Yes, I solved all the problems in contest, and I'm gonna go through the solutions of all of them eventually. And yes, problem F is amazing. So stay tuned for problem F. Well, I guess there were no more questions for problem C. So we will move on to problem D. In problem D, we needed to calculate the number of good subsequences, and subsequences called good is if some weird thing is true. So subsequence b1, b2, and so on, bk is good if k is at least 3, and for every t that is at least 3, yes, between 3 and k. Let's write it like that. bt is equal to b2, the second element, plus the sum of the first t minus 2 elements. So this is the definition of a good subsequence, and then we need to calculate the number of good subsequences, and was up to 1,000. So this sounds very weird, like why it would be a second element. The sum is not up to t, but up to the previous element. So we kind of want to understand what this is. And well, let's try to do it. So if t is 3, b3 is equal to b2 plus sum of bi from I from 1 to 3 minus 2, so it's just b1. Okay, b4 is b2 plus b1 plus b2. And then b5 is b2 plus b1 plus b2 plus b3. Okay, that doesn't look helpful. Although, like, this does look interesting. Like, so b3 is just the sum of first two elements. But then, if you just use the definition, it doesn't look like anything good. And well, jumping ahead a bit, my approach in general is that, like, you need to try to understand what the problem is about, maybe make some reductions, make it simpler, and then look at what you want to calculate. But like, you can work from both sides, and you can see, well, okay, I need to calculate the number of subsequences, and is up to 1,000. It's probably some dynamic programming, right? Like, we want to choose elements left to right, and, like, somehow maintain that it is good. So to make it work as a dynamic programming, we want our state to be, like, something smaller than just store everything. So, like, ideally, it would be nice if this condition would just depend on a couple of previous elements. Then we can, like, store the last elements, like, as much as we need, and when we do the transition, we, like, forget about the last stored element, because it is not important anymore for the further elements. But, like, this formula doesn't look like it because we have, like, the sum of all elements. We can actually try to say, okay, let's just store the sum of elements. So we can try to, I don't know, we can try to store b2, store the sum of previous elements, and then when we, like, do some transition, we need to add one element to that sum. So it is okay, it is a constant number of elements that we need to store, but it is like a constant number of integers, but the integers themselves can be big, and I don't know, it just doesn't look good. What we can do instead is try to modify this formula to do something, like, to make it better, and the way to do it is to, well, you saying that, like, we can maintain that sum and just add one element is already a pretty good step. So let's try to see what happens if we look at the next element. So this is the formula for bt. What will happen if we look at bt plus 1? So it is b2 plus the sum of elements from 1 to, like, t plus 1 minus 2. This sum is the sum that was previously plus one new element. So it's b2 plus from 1 to t minus 2 bi plus bt minus 1, right? The last element, the new element we added to the sum, the last one will have the index t minus 1. And then this thing is just bt, so this is bt plus bt minus 1. So actually, our condition is that the element with index t plus 1 is equal to element with index t plus element with index t minus 1. For all, like, that will work for t at least 3, so this formula works starting from element number 4. but for element number 3 it is also true. So these are actually just Fibonacci numbers, well, with arbitrary first two elements, but then every next element is just the sum of two previous elements. Okay, so turns out that this weird formula just defines pseudo Fibonacci sequence, and we need to calculate the number of subsequences that are it's kind of Fibonacci. Now we can do dynamic programming because we only need to store two last elements in the subsequence, because only on that will depend like can we take the next element or not. So we can write dpij, the number of subsequences that last element is element number j and the previous element is element number I, and then to make a transition we iterate over new element index k, but we can make this transition if and only if ai plus aj is ak. Okay, that is a correct solution, but it works in n cube. Which is a bit slow. I don't know, actually. Maybe it just passes. Like it's n cube divided by 6. There are like model operations. I think it should work actually. But we can do better. And the like how to do better is to say that instead of storing this dp by the indexes of last two elements, instead we can store them by the values of last two elements. So we can store a different, well, kind of array, I guess it is a map, dp prime of ai aj, and then when we try the pair jk, we know ak, we know aj, so now we know that ai must be ak minus aj. So we can just look up the number of subsequences that end on that pair, the pair being ak minus aj and aj. Just like look up the dp values that start for this pair, and this will be the new like number of sequences that like to which we can add element k. Actually, I now see that it is not exactly correct. If we have a lot of equal elements, like I guess we need to store like this one as a value and then just j. So the number of sequences that end up on position j and the previous element was x. So here put j. Yeah, that should work. But I wrote it incorrectly and got accepted, so I guess the test suite. Right, but now it is so we try those two positions, and we need to access like a map, so it is n square log. You probably don't want to have an actual map here. I had like the numbers that we will use are just elements of the array, so we can sort and unique them and then find the position sorted array with a lower bound and stores the DP as just two-dimensional matrix. The complexity is still the same, but the constant factor will be much better because maps are slow. But in any case, this is our final complexity. I guess if you use like an ordered map, it will be n square, but don't use an ordered map. It is dangerous. Any questions about problem D? Okay, if you don't have questions, you can send some reaction so that I can see that at least somebody is still watching and you understand everything and the stream is still working. Because otherwise, I have no idea. Great. There are no reactions, no comments. Okay, there is a reaction. Cool. So we can move on. One smiling face is enough for me. Problem E, we're given a 3 and was up to 200,000 something. Every vertex has some value in it. The values can be negative. So I think it was good. We can do some operations on this tree any number of times we want. One operation is to choose a path of length 3 and then we contract that path into one vertex and the weight will remain the weight of the middle vertex of the path and like if we had some other neighbors after we contracted into one vertex, those neighbors will be connected to this new vertex. Well, the statement says that they will be connected to the middle vertex, that's the one we keep, but like you can imagine it as merging those three just in one blob, but it is important that the weight stays the new vertex will have the weight of the middle vertex. The sound is low. Well, I guess I'm just speaking not very loudly. I'm sorry about that. I don't think I can increase it artificially. So I guess just increase the volume on your device. Right. So with those operations, we can apply them many times, and then we will have a tree with possibly smaller number of vertices. Um, so like some vertices will be removed, and we want to maximize the sum of weights of vertices that are remaining in the tree. Okay, so the approach in this problem is to say that for every vertex of the resulting tree, like, it is merged from some vertices, and those vertices were connected. So basically, if we look at the initial tree, there will be components that like eventually will be contracted, and from each such component there will be just one vertex that is remaining, and each component, it was something, some connected tree, and now we only have one vertex in it. Some components can be just one vertex, like it was one vertex, don't merge it with anything, just one vertex stays. Something. And whether we can take this connected component and merge it into this particular vertex, it doesn't depend on everything that goes outside. Like, we can just look at this tree and the chosen vertex, and we can try to understand whether it could be the case that this was a component and now it is merged into this one vertex. So let's try to find conditions for this to happen. And actually a lot of what I have drawn is not possible. I guess everything except for those two. But we can fix it. So now those two are possible, but those two are still not possible. And why is that? Well, let's see. So there should be like one middle vertex that will stay. And something can be connected to it. So what are the obvious conditions that should be true? So the first obvious condition is that size of this whole thing must be odd. So 1 modulo 2. Why is that? Well, because in every operation we remove two vertices, so the parity doesn't change. In the end we want to just have one vertex, so initially it must have been odd. And another condition is that assuming there was at least one operation, there would be a last operation, and the last operation must have had this vertex as the middle one. So either size is just 1, so we didn't do any operations, or our red vertex has at least two different neighbors in that must be merged into its component. So the size must be odd. That's clear, I hope. And sorry, and either the size is 1, so it just was one vertex, or this red vertex must have two different neighbors for the last operation to happen. And now I say that those two conditions are actually sufficient. So it should be clear that they're necessary, and we will now show that they're sufficient. And like this is a general strategy for many such problems. You try to understand some simple necessary conditions, and then like when you can't find anymore, you can try to prove that they're sufficient, or just believe in it. I don't know. Doesn't always work. Sometimes the criteria is difficult, so you cannot just find some simple necessary conditions and they turned out to be sufficient. But in many situations, when the problem is solvable, and even more so when it is solvable fast, when the limitations are big, the criteria is usually simple. Although, like you kind of need to correctly choose for which object you want to find the criteria. In this problem, I first tried to approach differently. Instead of like choosing the components and one vertex in this component, I was trying to just look at the set of those red vertices that will stay, and all the remaining vertices are between them somewhere, and I wanted to understand whether this set of red vertices is viable, and it looks like the condition for that is difficult. But when you like instead split into components and in each component choose one red vertex, turns out that the condition is pretty simple. Okay, now we want to prove that it is sufficient. And well, it is pretty simple. If size is 1, then obviously it is possible if we have at least two different trees. In every such component, we can just take path of length 3 and contract it while we have at least 3 vertices, because we don't care what will remain. We want to just reduce the number of vertices. So we will have some groups of either 1 or 2 vertices. Because if we have at least 3, then we can reduce the number by 2. So reduce those neighbor components to 1 or 2. And now, since the parity is correct, it means that like the total number of vertices is odd. So without our red vertex, it is even. And now we just want to pair those elements and kill them through the middle vertex. And it is always possible. The parity is correct. The sizes are at most 2. It is kind of well known that for making such pairs from different sets, for this to be possible, we need 2 conditions. The total size is even, obviously, and it is not true that there is a component that is bigger than all others. This just cannot happen here because the biggest component has size 2. So obviously it is not bigger than everything else together. Since we have at least 2 different components. That's important. Okay, so now this is our necessary and sufficient condition. Um, and it turns out that we can do dynamic programming on tree um, to find the optimal way to do it. Um, what there is a comment your cam. What does it mean? Camera? I think it's working. What's up? Is something wrong with the camera? Camera is slightly covering what you have written. Okay, yeah, I get it. Sorry about that. Um, was it anything important? I don't think so. Okay, so we have the criteria. Now we want to do a tree dynamic programming to choose the best split into components and red vertices inside the components, so that the sum of values in the red vertices is maximum possible. It is a bit tedious, and there will be a lot of cases, or like um, a lot of possible states, but like I will tell the overall idea and what are the states, but I guess I will not thoroughly prove that everything is enough. But okay, let's try to do it. So when we're doing a sub 3DP, we want to be standing in some vertex, and we want to somehow describe the current situation. So we are standing in this vertex. There is a path up from it. There is a subtree of this vertex. We have already chosen some components here and the red vertices, and like for the components that we have fully chosen, it doesn't matter anymore for us. We have made the choice because like what we are doing is splitting into like components, and then in a component we're choosing one red vertex, and then those components do not affect each other in any way, shape, or form. But there is a component for our current vertex, and it will contain some part of what is below, so some part of sub3, but it will also contain something that is higher. So what is important for us? We need to check that those things are satisfied, and also it will be important like whether where our red vertex is. And it is also important for the second condition. It is important for the value of dp, and it is important that we need to choose exactly one red vertex in the component. So what are the options? Where can red vertex be? Option 1, it is somewhere below. Option 2, it is somewhere higher, or like outside of our subtree. And option 3, our vertex is the red vertex. So in all those cases, we need to see what is happening. So let's say case 1. Case 1 means that here's our vertex. Everything that is higher will be all blue. From this vertex, like it has some suns. In one of those suns, so in those suns, we will take some part into our component, and in one of those parts there is our red vertex. And like it is also possible that for some sun we just cut it off completely. It is the sun is in different component. Okay, so in this situation, like well, first, what is important for us? Obviously, the parity of the number of chosen vertices is important. So we will always have a parameter that is parity. And we need to think about this. But like in this case, either we have already failed that, or like it is already satisfied, because like here's our red vertex. It might have had some suns lower, and like on the path up, now here's our higher component. So we just need to check that when we create that red vertex, it must have had at least one sun in the component that is lower, and we will go up. So right now it just means that after we end processing this vertex, like this state we just need to know that the red vertex was below somewhere, and parity of size. Parity of size will be just like a separate parameter in the DP. So I wrote this once. It will always be present. So like this is just a description of the state. The red vertex was somewhere below. In the second case, if the red vertex is somewhere higher, it means that everything that is below is just one blue component. So there is a second option. The red vertex is not present yet. So this is option 1, or let's say option A, because I used numbers for cases. Option B, no red vertex yet. And in case number 3, so we are creating the red vertex now. Our vertex has some children. In some of the children we just cutting. In some of the children we are taking the blue components of it, the option B from there. So there is something that will correspond to like that will be in the same connected component, but there are no red vertex here. So when this is a red vertex, this is case 3 kind of, we are choosing like for every sun whether we are taking something with case B or not. And if we have so again looking at our criteria, the parity is done by parity flag, so we do not bother about this. But this is pretty difficult. Like, we need to make sure that this red vertex has at least two different neighbors. So in this case, it does have, but maybe we did not take this edge either. So now we just have one neighbor. It means that we have to take somewhere here. Have to take something from up. So that will actually be another option. Like in this case, yeah, the red vertex was below and we don't need anything else. Like we can stop right now. But there is an option C. Red is below, like in option A. But we need, like, we must take the parent inside our component. And there is also option D when the size is 1. Option D, it's just one red and nothing else. So we're just saying this vertex is red and it is in the component of size 1, so we didn't take anything from the suns and we are not allowed to take the parent. So there it must start a new component. Okay, so those are our 4 options that are distinct, and it turns out that it is enough with parity also. For this option there is just one option of parity because the size is just 1. So like total number of options is 7, ABC with both parities and D with one parity, but like it is I think it is simpler to implement when you have like 4 options and additional parameter of DP that is parity, and one of those 8 will be just like non-viable. It will always be it's just unreachable. So this is our 4 options, and now for all 3 cases we need to understand how to make transitions. To make a transition we will have like another inner DP basically. Like we are adding, we're going through children one by one, and for every child we're making a decision and that affects our current state. So the simplest case is case number 2, when the red vertex is outside, then like our vertex must be blue and everything below also blue, so it's simple that we're just looking at the like option B for every sun, and also in every sun there is an opportunity to just cut it. To cut it, it must be either option A or option D, because it must be a correct component. B and C are not correct. B is not correct because there is no red vertex, and C is not correct because it promised to take the parent, so we cannot cut it here. So B and C are not correct. A and D are correct if the parity is correct. So A and D with correct parity, we can just cut it here. So for every sun, we can either cut it and take like ND, or take option B and like also update the parity correctly. So that was the simplest case number 2. Case number 1 means that like it is drawn here. Now for every sun, again, we can cut it, which is the same as previously. But among the suns, there must be exactly one where the red vertex is taken. So for other suns, it is the same. For this one, it must be either option A or option C. They're the same now because we're taking the parent, so it is fine. So you kind of need, like, for the inner DP, you need an additional parameter how many subtrees with red vertex inside we have already taken. And in the end, if we have taken 0, it will be case number 2. If we have taken exactly 1, it will be case number 1. If we have taken more than 1, it is impossible, so we just don't store it. And the case number 3 is the hardest, but it's also not that bad. So we are saying that, okay, this vertex itself will be red. Going through the suns, again, we can just cut it as in the previous cases, or we can take option B in the sun, no red vertex yet, but we need to count the number of suns that we took to make sure that this happens. So if we have taken at least 2 suns, it doesn't matter anymore. So basically our options for the number of suns we have taken here are 0, 1, and 2 or more. So we can, this again will be a separate parameter in the inner dynamic programming. And you can do the updates. Like when you cut it, you don't increase it. When you don't cut, you take the sun, you increase it by 1, unless it is 2 or more, in which case it goes to itself. And in the end, when you process all the children, if you have taken none of the children, you can use option D. So it's just one red. We don't take any of the children, but we also cannot take the parent. If you have taken one child, then you will get option C, because we created red vertex in this component, but we still need one more neighbor, and it must be our parent, so that's the definition of option C. And if you have taken at least 2 children, then it is option A. The red vertex is inside, and we can either take parent or not take it. It's fine both ways. That's it. Like I know it's a lot of options. Like we have 4 options in the states. We have 3 options for the transitions. That's what I have written. It is not that hard to implement, like if you understand all the cases. And like, the solution is, the complexity is O of n. It's just like big constant, making like all those constant number of parameters and transitions from every state, but it is still linear in total. That's it for problem E. I understand that it's a lot, but I don't know. I don't know a simpler way. Like it is a class of problems when you do like 3GP and there is constant number of possible states, and you just analyze how the states change depending on the actions you do, and the code always looks the same in them. It's just like one DFS that does a lot of case by case transitions. Um, but it is not that difficult if you have experience in those kind of problems. Um, you can ask your questions. Um, I will read the comments that happened below before that. Hi, Unik, I miss you uploading Div1 screencast videos. Hello, I'm sorry about that. I updated macOS like 2 months ago, and the the software I was using for recording screencasts, like it works, but the camera feed stutters when I switch between screens, like go uh, from Sublime Text to browser, for example. It can be fixed, like I can press on it and it will go to normal, but it distracts me from the contest, so I'm just not doing it. I can try to find some alternative, like I guess I can use OBS since it works pretty good right now. I can use the same for the contest. Yeah, maybe at some point I will manage to do it and go back to posting screencasts, but for now, the the workflow I was using is not viable anymore, so I just uh, put the screencasts on hold. And the second question: what will be the approximate difficulty of this problem by KF standards? I don't like the questions like give the difficulty rating, because I don't know how that works. Like, what does that number mean? It is a relatively difficult problem, but it is like standard. I don't know. It would be like C or D in Division 1. But it is tedious to implement. And like it's not simple to come up with all the cases, but when you just sit and like, go through all the possible cases, it is very doable if you have experience in approaching this kind of problems. Yeah, so probably C or D in first division. I can definitely see this problem as like last in second division, to make sure that nobody from second division actually solves everything. Because it is probably like on the edge of possible to solve for like purple. Alrighty. Please send some reaction so that I can move on. Oh yeah, we just lost like half the viewers. Great. So nobody will send the reaction. Big fan. Thank you, I guess. Oh. Problem F. Yeah. So this one I think is the most beautiful problem in this contest. For a long time, I thought that I must misunderstand the problem because like this looks impossible to do. But then when I looked at it from a correct angle, it turns out that it's not that hard actually, but like yeah, it is a difficult problem for sure. Um, so let's recap the statement. There was a rooted tree. Again, in every vertex there is a value. Values can be negative. This time they were up to 10 to the 6, for which I'm grateful. Like it wouldn't be a very big deal if they were up to a billion, but it was easier to implement with smaller numbers. Root 3, and the root is vertex number 1. We want to erase all the vertices, and what we can do, one operation that we can apply is choose vertex such that the set of vertices in the subtree this set, like by IDs of vertices in the subtree, so this set is a set of consecutive integers. Then we pay AV and delete all the subtree. In that we want to delete all the vertices, we want to minimize the cost, which can be positive. I mean, the cost can be negative, so our convenience might be positive. Okay, so it kind of looks like we want to do some kind of dynamic programming again, but it's not clear how to do it at all. I mean, you can define dynamic programming. What is the cost to delete a subtree of vertex? But the transitions look very difficult. Like we have vertex v, there is subtree. Then we need to choose what we have cut previously. So we have cut this, and this. And all the remaining numbers must be a set of consecutive integers, and then we can remove everything. And like the cost will be like AV plus the DPs in the roots of those things we have removed previously. I don't know, looks impossible to. Oh, sorry. Can I undo? Yes, I can. Looks impossible to do anything with it. So instead, what we want to do is to say that the fact that the tree is rooted is not very important. Like it is still somewhat important for the cost functions, and we will need to handle it, but we can more or less ignore that the tree is rooted, and what we actually want to do is to split the tree into components again. I guess like similar to problem E. uh, such that every component is a set of like in the component the IDs of the vertices are a set of consecutive integers. If we do that, it turns out that, well, we can always choose an order in which to remove them, such that we removing those components in some order. So um, split into some components. Now, like this tree uh, can be rooted in one, but on the components we also have a tree, so we can root the tree by the component in which the vertex number one is located, and then just go from lower levels to higher and remove the components one by one. So like we can cut this component by applying the operation in its highest vertex. Then we can cut this component, then this, and eventually this. So instead of like applying this iterative process of choosing a vertex, check that everything below that vertex is a set of consecutive integers, then delete it and proceed, we can say, okay, instead, let's choose which components we will remove, and then we will just there will be an order in which they can be removed, and we can define the cost of doing that. So how to define a cost? Well, the cost must be the number that is written in the like root of subtree when we delete it. But what is root of subtree? Well, it is just the highest vertex in the subtree. So cost of component is AV, where V is the highest vertex in the subtree, or you can say that it is an LCA of the subtree, which will be the same thing because the subtree is connected. Okay, but that's still like it looks like the same thing as previously. Like we're still having those trees, and like if we're doing dynamic programming on tree, then it will be the same. But we don't have to do a dynamic programming on tree because for every component we know that it is a set of consecutive integers. So if we just look at vertices in order from 1 to n, then each component will be a segment, and actually like this split into the components is the split into segments of this order. So we are choosing the segments. Each segment must be a connected component in the tree, and we need to separate this whole array from 1 to n into those segments. So instead of splitting the tree into the components such that each component is a set of consecutive integers, we will flip it on its head and say that we want to split the integers from 1 to n into segments such that each segment is connected. in the tree. Okay, now it looks at least plausible that we can do something with it. Like, we can definitely do a dynamic programming that will store like up to which point we have split everything into segments, then we choose the next segment, and at least we can achieve something like n cube, right? Like we're doing dp of prefix, then iterate over the right border of the next segment, and then for this segment we need to look at the vertices with IDs from this segment and check that it is a connected component, and look up what is the highest vertex on that segment. So that would be n cube, which is already incredible. We got to a point where we have a polynomial solution. Now we can try to speed it up, and like, it's already good that the number of states is just linear. So we just need to make transitions faster, or much faster. We have n squared transitions. We want to make them faster than in constant time per transition. So I guess we would need some data structure. And like the properties that we want to achieve in that, like we need to check that the vertices from the segment are a connected component, and also the cost depends on the highest vertex among those. But there are trick plays that will allow us to achieve that. And like those trick plays I have seen before. They're pretty cool, and like it's probably hard to come up with in contest setting if you haven't seen them before. But like for me, from the moment I got to this idea, like to get into fully formed idea, was like, I don't know, 10 minutes, and then 10 more minutes to implement it. So for me, like this is the most important and mind-blowing step. The rest is like applying standard techniques, more or less. So the standard idea here is that how to check that something is a connected subtree. Well, it is a part of a tree, so if it is connected, it must be also a tree. And we can say that being a tree is the same as the number of vertices minus the number of edges is 1. Then the number of vertices is just the length of the segment. So what I want to try to do, look, let's for example try to solve the problem of like counting how many segments are there, such that this vertices with IDs from the segment are connected in the tree, which is a problem that I have solved previously. So the idea will be we will do a scan line from left to right, maintaining the like current right border of the segment, and for each left border I want to maintain in some data structure what is the number of edges that exist like on the segment with this left border. How to do that? Well, what does it mean that the edge exists on this segment? It means that both endpoints of that edge are on this segment. So when we are in the right endpoint of an edge, we will look, okay, here's the left endpoint. So if the left border of the segment is on this prefix, then this edge exists now, because our right border in scanline have reached this point. So like all of our segments will have right border after this. So this edge exists if and only if the left border is on this prefix. So if we want to count the number of edges that exists like for this left border, we need to do +1 on this prefix. Okay. Instead of counting the number of edges, we can maintain this thing. So it is basically the same. When we move right border in the scan line, we add 1 to all the segments, because like for every fixed left border we have added 1 vertex. We have moved right border of the segment to 1 to the right, so that creates new vertex on all the segments. Then we iterate over all the edges from that vertex. We only consider the edges that go to the left, and for each such edge we do -1 on this prefix of left borders. So now for every left border, we have fixed right border in the scan line. For every left border in the segment tree, we have value v minus e. And the segment is good, it is connected in the subtree, if and only if it is equal to 1. Equal to 1 sounds hard. Like that is not something segment trees can do. We cannot like add something on segment and then calculate the number of values that are equal to 10. That is not an operation that is available in the segment tree. But what we can do in the segment tree is to count the number of minimums. So we will write a segment tree on minimum that counts the number of minimums, and then like ask what is the minimum and how many times it appears here. And I state that all of the values that are here, like our v minus e, are at least 1, because it is a tree, so we don't have cycles. So if we just choose some set of vertices, we cannot have more than v minus 1 edges inside that set. So v minus e is always at least 1, and we are interested in when it achieves the minimum value, the 1. So that segment tree can do. Now if we go back to our problem, it looks like we should store like segment tree on minimum of GP values. Like that's how we want to update GP, right? We want to calculate minimum over like GPL over all viable L. And viable L means that v minus e is 1 for this left border. So for this thing, let's like we will store segment tree on GP, but we will also add like v multiplied by infinity minus e multiplied by infinity, where infinity is just some symbol for like some big number, 10 to the 12th power, so that it is bigger than every possible answer, because answer is bounded by the sum of AV. So now we can add those things. We can maintain them similarly to how we would solve the problem about just checking which segments are connected. So do the same scan line, do the additions of this infinity when we move right border to the right. Then for each edge we add minus infinity for the prefixes. And that would mean that for all the viable states where v minus e is 1, we have added one infinity. But for all the non-viable states, we have added at least two infinities. So they will not affect the minimum value. So when we take the minimum, it will be infinity plus the best of dp's of the viable positions, or it will be at least two infinities if there are no viable states. Okay, that almost looks like what we want, but we have not considered how to like add the actual costs of components. So we have considered how to kill the states that are not viable. But we also need to like actually add the cost of the component. And to do that, we will do something similar. So this thing basically says we will add one for, like, we will add infinity for every vertex, but then subtract infinity for every edge. And if the number of vertices is exactly one more the number of edges, it will be just one infinity, otherwise it will be more than one infinity. And those are actually the distinction between connected sets and not connected sets. We can actually make it a bit more granular, and we can say that, okay, for every vertex, let's add AV, but for every edge, let's subtract the points for the lower of the two vertices. So if we have some set, and we add up the AV for all the vertices, but then for all edges we subtract the lower one, we will be left with only the A of the highest vertex in that set, assuming that this set is a tree. But that is already checked by like our global thing. So in the same segment tree, when we process a vertex, instead of adding just infinity to all the left borders, we will add infinity plus AV. And when we process the edge, we will subtract infinity just because it's an edge, and also subtract A of the lowest of the two endpoints of the edge. Now, for every segment, if it is not connected, there will be at least two added infinities. If it is connected, there will be exactly one added infinity, and also it will add the AV for the highest vertex in the set, which is exactly what we wanted. And now we just do this scanline, calculate dynamic programming, and we are done. And the solution works in nlogn. So like the code is super simple. You just have this one segment tree with addition on segment and minimum. You do scanline on the right border. For every vertex, you add infinity plus AV to everything, and then for every edge that goes backwards, you subtract infinity plus the A from the lower vertex of that edge. And that's it. Any questions about problem F? If you don't have questions, you can just send some reaction so that I know that I can move on. I would have too many questions. Well, you can try to ask some of them. Yeah, this is a difficult problem and also a beautiful problem. Benefits of having a recording. Right. I'll I'll take another drink of water, and if there are no more questions after that, we will move on to problem G, which should be pretty fast. Okay. Problem G that changed limitations during the contest, which is not cool. We had a directed graph. And each edge has a weight. And we can walk on that graph, but actually we can walk like against the direction of an edge. And if we go along the edge, if we go along the edge, we add v. If we go against the edge, the direction. Against the direction, we subtract v. And we say that the assignment of weights is good if it is impossible to do a cyclic walk of a non-zero total weight. Or I guess it says if it is impossible to do a walk of negative. So good means that impossible to do a cyclic walk of negative negative total weight. We can change some weights for if we want to increase or decrease it by one, we pay 1 coin. What is the minimum number of coins we need to achieve a good configuration? So first we need to understand what is good, and it is pretty well known, and it is even well known outside of competitive programming algorithms. Actually, you might know this from physics. Like this is basically the condition under which you can introduce a potential function. Like this is how energy changes when you move from one place to another. And if it is if on every cycle the sum is 0, then you can introduce a potential function. So this is actually the same as you can introduce potential function from vertices to numbers such that any walk from V to U has cost potential of U minus potential of V. And basically the same would be for every edge. If we have edge VU, then weight of this edge is potential of U minus potential of V. So how do we prove it? Well, if it is impossible to do a cyclic walk of negative total weight, it is also impossible to do a cyclic walk of positive total weight, because if you have a cyclic walk of positive total weight, you can reverse the direction you walk in and you will get negative total weight. So this actually is the same as every cyclic walk. Total weight is 0. Then you can look at every connected component basically separately, because you cannot walk from one connected component to another. And in the connected component, you can just calculate this potential function by saying, okay, in some vertex it will be 0, then start walking and assign potential so that this holds. Like when you walk through an edge from V to U, you say that, okay, potential of U is potential of V plus weight of edge. And this potential function will be consistent, because otherwise, like if you find an inconsistency, it means that you have found a cyclic walk that the total weight is not 0. So good situation is equivalent to existence of such potentials. Now we can reformulate the problem in terms of potentials. We want to basically we want to choose what potentials will be in the end. Like we want to change weights of edges such that the situation is good, but when good, we can define potentials. So let's just choose potentials, and then based on those potentials that we have chosen, we know what weights of edges we want, so we just go to them directly. So we want to choose potentials for all vertices. Then like the end weight of an edge must be this. And the cost to achieve that end weight for the given edge is absolute value of initial weight minus the weight we want. So the total cost is sum over all edges the initial weight of that edge minus the difference of potentials. Okay, so this is our target function and we want to minimize it. Great. Now we can kind of forget about all of that. I'm just rewriting the formula from the bottom. Okay, the potentials must be integers, but let's ignore that, and let's just say I will not prove that we can ignore integer property. It shouldn't be hard, but it's probably tedious, and I haven't thought about it. So I will just say that okay, we can allowing ourselves to do like non-integer changes to weights and non-integer potentials. So now I want to say that this target function is linear. It is not exactly linear, like the absolute value makes it non-linear, but we can make like I forgot the word. We can make some dummy variables such that this will become linear. How to do that? Let's say that for every edge, I want to choose non-negative values x and y, such that this thingy lies between minus xe and ye. And now, instead of minimizing the sum of those absolute values, we will minimize the sum of xe and sum of ye. Basically, if this is positive, then ye must be equal to this value, or like at least this value. And since we want to minimize it, we will just set it equal to this, and xe will be equal to 0. And if it is negative, then xe must be equal to minus this value, and ye will be 0. So this is the same. The limits that are that they're at least 0 are also important. And now this is an instance of linear programming problem. There's probably simpler and more direct way to do it without using linear programming. At least like you can kind of guess what you need to do, but for me it is natural, and it is what I have done in contest. I have written this in this way. Now I get a linear program, and now we will write a dual to this linear program and look at it. So we have 3 types of variables. Our potentials phi that we have for every vertex. Let's also, I guess, let's rewrite them with indices instead of functions. So it's phi u minus phi v. And the potentials can be anything. So x and y are non-negative, the potentials can be negative. So our variables are phi x, y, phi for vertices, x and y for edges. Those are the inequalities we have, and this is our target function. Let's also rewrite inequalities so that we have all the variables on the left and all the signs less than, because we have no, not less, greater. All the signs must be greater because we have a target function for minimum that will help us write correct dual program. So for this inequality, we want to move the variables on the right because we want greater than sign for variables. So it will be xe minus phi u plus phi v greater than or equal to minus v. And for this, I'm moving to the right. So it's ye plus phi u minus phi v at least ve. Okay, so those are our inequalities. So to write a dual linear programming problem, we need to introduce variables for every inequality. Our inequalities are connected to edges, so I will use edge as an index. So for those inequalities, I will introduce lambda e, and for those inequalities, mu e. And now we will have inequality for every variable of the original program. Also, since our inequalities are of correct sign, that means that lambda and mu must be non-negative. So now for every vertex we had a variable phi of v, which appears in both those inequalities for every edge that we for which we have it. So so the corresponding inequality here will be or actually it will be an equality because phi is not bounded, so it will be equal to the coefficient from the target function, which is 0. So we will have something equal to 0, and that something must be sum of all over all edges that go from v. We have lambda with plus sign and mu with minus sign, so it's lambda e minus mu e, and over all the edges that go to v, it is the other way around. Yeah, if you have no idea what I'm doing, what is linear programming, what is dual linear programming problem, then this analysis is not for you. Like I'm just using heavy machinery that is well known. Like this linear program, for linear program we can write dual program. So I'm just applying knowledge of humanity. Okay, for variable phi we wrote it. For variable x, it appears only in this inequality, so it would just be lambda e is at most, because our program will be on maximum, And on this side it should be the coefficient from the target function, which is 1. And symmetrically for ye, that mu e is also at most 1. And our target function must be the sum over all variables, them multiplied by the corresponding free coefficient, and we need to maximize it. So it will be sum over e lambda e multiplied by minus v plus sum over e mu e multiplied by ve, and we want to maximize it. We can rewrite it a bit. It will be sum over all edges of ve times mu minus lambda, and to maximize it. And we can see that basically all our basically we are not interested in mu and lambda by themselves, so we can introduce a new variable for every edge, mu minus lambda, which we will call, I don't know, f of e. And then from those inequalities, it means that f of e is between -1 and 1. Because, yeah, lambda and mu are not greater than 1, but they're also at least 0. So they're between 0 and 1, which means that f of e is between -1 and 1. This will be transformed into the sum of f of e over all edges going from minus f e over all the edges going from e plus sum of f e over all the edges that arrive into e, and it's a 0, and we want to maximize this. Okay, great. Is it visible? Is it not? Yeah, it is not hidden behind my camera feed. Great. So this now is. It should be very visible that this is a flow problem. I even called the variable f. So on every edge, we want to assign some flow such that for every vertex, the sum of minus flow over all the edges that go from that vertex plus the sum of flow over all edges that go to that vertex is 0. So that is conservation of flow. And we want to maximize sum over all edges, some coefficient from that edge multiplied by flow. So this is like max cost flow. We don't have sink and source. So this is not a like flow problem. It is I forgot the word again. No, seriously. So it's a flow problem without source and sink. And the flows are just going on cycles. And we want to have maximum cost. Usually we want minimum cost, which is achieved by just multiplying all the weights by -1. Um, and yeah, there are max flow algorithms that can solve this problem. And like, actually, it turns out that the solution is just take the graph that is given in the statement and find I remember the word circulation. Find mean circulation on that graph, more or less, um, and that value is just the answer to the problem. But the way I got there is to say, okay, there will be potentials and vertices. Now we can write target function like this. Now we can introduce dummy variables and get the linear program. Now write a dual program. Turns out it is a max circulation problem. Great. Copy paste some fast flow from library checker and you're done. That's my solution to problem G. It might be true that there are some more insightful solutions. Like, you can probably somehow explain like why do you just need max circulation on the initial graph. But that's how I did. Any questions about problem G or about any previous problems? If nobody has any questions, then we can finish. Thanks for watching, thanks for coming to the stream. Goodbye.